Welcome to the Deep Dive. We're here to sift through complex information and pull out the key insights for you.
And today we're diving into something pretty fascinating.
Yeah, we're looking at this surprising link between ancient Greek philosophy and, well, cutting-edge artificial intelligence.
It sounds a bit unusual, maybe. Plato and AI.
Definitely. But we're going to explore how AI actually represents knowledge. And it turns out that's a much deeper, more philosophical question than you might think at first glance.
Exactly. It gets right to the heart of how these systems think, if you can call it that.
Our main guide for this journey is a paper, Plato to AI, Abstract Knowledge Representation by Gerardo Jovan and Giovanni Ovani. They really map out this connection.
So our mission for you today is basically to unpack this idea that AI's way of handling knowledge has deep roots in Plato's concepts.
We'll look at how that actually plays out in AI systems, the practical side.
And understand the benefits, because there definitely are some powerful ones.
But also, critically, look at the limitations, the really profound ones.
We want you to see not just how AI works technically, but why it's built the way it is.
And what that means for what it can do in the future. And maybe why it sometimes stumbles right now.
Right. So to really get this, we need to start way back with Plato himself.
Let's do it. Where do we begin with Plato?
Well, the core idea is his theory of forms. Plato suggested there's this metaphysical realm.
Like another dimension.
Sort of, yeah. A world of perfect, eternal, unchanging forms. These are like the ultimate blueprints for everything we see and experience in our physical world. The ideal versions of things.
Okay, ideal blueprints. Got it. So how does that connect to AI, code, and algorithms?
Well, here's the parallel our source highlights. AI uses data abstraction. It takes all this complex, messy, varied stuff from the real world.
Like thousands of pictures of cats.
Exactly. Thousands of cats in different poses, lighting, whatever, and it generalizes them. It creates universal templates or patterns.
Trying to find the ideal cat in the data.
Precisely. The goal, as the paper puts it, is to recognize stable forms behind unstable phenomena. That's absolutely key for pattern recognition.
So AI is essentially trying to find those stable, unchanging qualities, the essence of the thing, just like Plato's forms.
That's the core idea, yeah. It allows the AI to separate the ideal entity, the pure concept, from all the imperfect examples it sees in the real world.
Okay, that makes conceptual sense. But, how does an AI actually do that? Can you give us a concrete example?
Sure. Think about feature vectors. It's a common technique, especially in, say, computer vision.
Feature vectors. Sounds technical.
It's basically a list of numbers, like a numerical fingerprint for an object. It might represent consistent qualities for a cat, maybe its fur, texture patterns, ear shape, general silhouette.
So numbers that represent catness.
In a way, yes. This list of numbers, this vector, captures those stable qualities. It lets an AI vision system recognize the ideal cat pattern, even if the cat is sitting, running, partly hidden, whatever.
So AI, like Plato, is trying to strip away the noise and get to the unchanging essence. Makes sense why that was an early path.
It was a foundational approach. But let's dig into how this Platonic abstraction actually showed up in early AI systems and, crucially, where it started to show its limits.
Right, because those feature vectors you mentioned sound useful but not perfect.
Exactly. They're great for recognizing stable qualities, the whats, but the source points out a key limitation. They failed to capture the nuances of the specific and individual context, meaning the AI might know it's a cat, but it doesn't really understand how that cat is interacting with its environment or why it's doing what it's doing. There's a lack of interpretative depth.
Okay, so beyond feature vectors, what other early approaches had this Platonic flavor?
Well, there was symbolic categorization. This is where AI systems represent objects using simple labels.
Like literally just tagging a picture cat.
Pretty much. The image gets linked to a unique symbol for cat. This allows for what one researcher, Vadinsky, called essentialist form recognition. It recognizes the core essence, the catness.
And this was useful.
Oh, yeah. Hugely beneficial in fields like medicine. Early expert systems use this for medical diagnosis, classifying symptoms under disease labels.
But I sense a but coming.
There's always a but, isn't there? The big drawback was rigidity. Total reliance on these predefined abstract categories.
They're stuck in its ways.
Very much so. They fail to incorporate the nuanced contexts inherent to the real-world application of knowledge, as the paper says. You end up lacking the interpretative depth needed to bridge the gap between the neat category and the messy reality.
Like knowing the textbook definition of a disease, but not quite grasping how it affects this specific patient with their unique history.
Precisely. And it wasn't just simple labels. Formal ontologies were another big early approach.
Ontologies, like family trees for concepts.
Kind of, yeah. AI systems built these hierarchical structures. Think of organizing medical knowledge. Diseases branching to symptoms, linking to treatments, all in a fixed hierarchy.
Seems organized, but maybe too organized.
That was the problem. They relied on static systems of representation. Everything, the entities, the relationships, was predetermined, fixed.
Which means adding new knowledge is hard.
Extremely hard. It severely restricts their ability to incorporate new entities. Real-world knowledge, especially in medicine or science, isn't static. It changes.
So you'd need to constantly rebuild the whole structure.
Exactly, requiring real-time reconfiguration, a huge disadvantage. This Platonic rigidity, this static model, was a fundamental flaw. It just couldn't cope well outside very specific controlled problems.
Okay, so lots of early AI was built on this Platonic foundation of fixed, ideal forms. Clearly it had major limitations. But surely it wasn't useless. There must have been broader benefits, right?
Oh, absolutely. We shouldn't dismiss it entirely. Despite the limitations, this abstraction is what allows AI systems to reason and learn across different inputs in the first place. It provides efficiency and scalability.
It stops the AI needing to learn every single unique thing from scratch.
Exactly. And this power of abstraction is huge in, say, natural language processing, NLP.
Absolutely.
Well, think about understanding text. An AI can use abstraction to ignore irrelevant variations such as word choices or word counts when it's trying to spot a particular concept or phrase across different documents.
So it can see that buy a car and purchase an automobile mean basically the same thing, even though the words are different.
Precisely. It gets to the underlying abstract meaning, which is incredibly useful.
But this focus on the abstract, the stable, it leads to problems.
It really does. The flip side of only capturing stable qualities is that AI models can become overgeneralistic.
Meaning they apply the pattern too broadly.
Yes. Since these algorithms are essentially math equations trying to fit abstract templates, there's a real risk they fit inputs incorrectly, which ultimately hurts accuracy. It's like using a cookie cutter that's just slightly the wrong shape.
The ideal blueprint doesn't quite match the specific situation.
Right. And this is where we see major criticisms, both empirical from seeing AI fail in the real world and philosophical.
Like who?
Well, back in 1989, Daskal critiqued how these static systems struggle with the dynamic, interpretative processes of the mind. Human thought isn't static.
And those classical expert systems you mentioned, the ones based on just manipulating symbols.
Those often struggled to accommodate irregular inputs. They were built on rigid rules, the physical symbol system's hypothesis. If the input wasn't perfectly formed according to the rules, the system often just broke.
The square peg and the round hole problem.
Exactly. It couldn't handle anything outside its predefined forms.
And this ties into another big philosophical headache for AI, right? The grounding problem.
Ah, yes, the grounding problem. It's a really fundamental challenge still relevant today.
What is it, basically?
It's about giving internal meaning to the symbols AI uses. How do you make sure the abstract symbol, like the label chair, actually corresponds to, well, real chairs out there in the world?
So the symbol itself doesn't inherently mean chair.
Not inherently, no. It's just a token the system manipulates. Without a connection to actual physical chairs, maybe through sensors or interaction, the symbol isn't grounded in reality. It's just floating, abstract.
Like knowing the word red, but never having seen the color.
That's a good analogy. It highlights this need to connect abstract concepts to their practical instantiations in a context, likely through sensory experience, which AI traditionally lacked.
So these early static models were rigid, struggled with grounding. What else?
They were also fundamentally unable to adapt to unforeseen circumstances. If something unexpected happened, they had no mechanism to adjust.
And even the early connectionist models, the neural network precursors.
They were more adaptive, yes, but often lacked abstraction. They learned from data, but struggled to generalize well. And symbolic planners, AI designed to make plans, just fell apart if the inputs weren't perfectly clean and defined.
Okay, so the limitations were becoming really clear. Empirical failures, philosophical problems. The field had to change direction.
It really did. These issues forced a move towards more adaptive approaches and, crucially, towards hybrid systems.
Hybrid, meaning mixing the old and the new.
Exactly. Combining the strengths of symbolic representation, clear categories, the labels, with the power of neural networks, which are much better at handling real-world fuzziness, adapting, and scaling up.
Can you give an example of such a hybrid system?
A key example is Sun's Clarion architecture. It's designed specifically to allow knowledge to flow between a symbolic part and a sub-symbolic neural network-like part.
So it gets the best of both worlds.
That's the idea. The system can actually modify the abstract categories by empirical means. It learns from experience and adjusts its categories without throwing out its general knowledge structure.
So it mediates that tension you mentioned earlier between the universal form and the specific instance.
Precisely. It's a way to handle both the Platonic ideal and the messy reality. It can maintain general rules but refine them based on what it encounters.
This sounds like a big shift in thinking about AI knowledge.
It is. A major concept emerging from hybrid approaches is that AI knowledge does not need to be permanent, but rather is dynamic. It accepts that knowledge isn't static, it evolves.
That it feels much more human somehow.
You can draw an analogy to human language. We have grammar rules, that's our abstraction, our structure.
Right, the form of language.
But we use those rules incredibly flexibly. We can use countless different words and sentence structures to say the same thing, adapting dynamically to the situation. We manage both the abstract rules and the specific varied expressions.
Okay, so hybrid systems forms connect not just to AI knowledge, but also digital metaphysics. What's that?
Yeah, it's another interesting angle. The philosopher Steinhardt argued that computers themselves, being discrete and modular machines, are kind of like modern versions of Platonic forms.
How so?
Well, digital metaphysics treats algorithms as these abstract, universal entities. They exist independently of the hardware they run on.
So the sorting algorithm is the form, and running it on my laptop or a supercomputer are just different physical instances.
Exactly. The software implementation, the specific Turing machine model, those are just instances. They don't change the core algorithm, the form itself.
But does this view of algorithms as pure forms run into the same problems we've been discussing?
It can, yes, because it's still fundamentally based on abstraction. It might not fully capture all aspects of intelligence, especially the empirical experience-based parts, bringing us back to Dascal's critique about dynamism.
Which leads us back to this core issue of AI's understanding or lack thereof.
Right. Classical AI was great at encoding abstract knowledge mathematically. Machines could manipulate symbols, draw logical inferences. It fit that Platonic ideal, that dualistic view of knowledge, abstract thought, separate from messy experience.
But the big problem remains.
The crucial problem is, if all knowledge representation is essentially the capture of abstract forms, it leaves all interpretations in the dark.
It knows what, but not how or why in a given context.
Exactly. And if a system can't distinguish different interpretations of a situation, if it can't handle ambiguity or context, that lack of flexibility means it will inevitably break down for anything other than purely formal, well-defined problems.
Any system, human or AI, needs to handle interpretation to apply knowledge effectively, right?
Absolutely. So the conclusion we're drawn to is pretty stark.
I'll be honest.
Because AI, particularly in its classical forms and even with some limitations in hybrid systems, struggles to reason about interpretations. Its epistemology, its theory of how it knows things is incomplete.
And if its way of knowing is incomplete,
then its metaphysics, its model of reality, will always struggle to fully embrace empiricism, the grounded, context-rich experience that seems so vital for true understanding.
wow. So we've gone from Plato's ancient ideas about perfect forms, traced them through early AI's attempts at abstract knowledge, saw the benefits, the major flaws,
and arrived at hybrid systems that try to bridge the gap, but still face this deep challenge of interpretation and grounding. It's this constant tension between the clean, abstract ideal and the complex, messy, real world.
So hopefully you now have a much deeper sense of why AI works the way it does, this philosophical underpinning, and also understand the fundamental hurdles that still exist.
Challenges that have roots stretching back millennia.
Which leaves us with a final thought to ponder. If even today's advanced AI systems, these sophisticated hybrid models, still wrestle with grounding symbols in reality and reasoning about interpretations, what does that really mean for the quest for artificial general intelligence for truly human-like thinking machines?
Is complete intelligence even possible without that deep, almost intuitive grasp of context and meaning that humans seem to possess? Or is there another paradigm shift coming, something that will finally bridge this ancient philosophical divide?
What will it actually take for an AI not just to classify or predict, but to
Good.
truly understand?